Hi, I'm Rudini Sampaio from Pargo Research Group in Fortaleza, Brazil. I'll talk about hardness of variance of the graph coloring game. This is a joint work with Thiago Macilon and Nicolas Martins. In a proper coloring, the vertices of a graph are colored. Two adjacent vertices must receive distinct colors. Key of G, the chromatic number, is the minimum number of colors in a proper coloring. A greedy coloring is also a proper coloring. Colors are integers. We take an ordering of the vertices. A vertex must receive the minimum available color. Gamma of G, the Grundy number, is the maximum number of colors in a greedy coloring. Since this is a proper coloring, gamma of G is at least key of G. We can imagine that we have two players, Alice and Bob. Alice wants to minimize the number of colors. Bob wants to maximize the number of colors. If Alice plays alone, she gets key of G colors. If Bob plays alone and the coloring must be greedy, he gets gamma of G colors. In the graph coloring game, Alice and Bob alternate turns, given a graph G and a set C of integers representing the colors. Alice wins if all vertices are successfully colored. Otherwise, Bob wins the game. From Sermerlo von Neumann theorem, this is a finite perfect information game without draw, then Alice or Bob has a winning strategy. Then the game chromatic number is defined as the minimum number of colors such that Alice has a winning strategy in the graph coloring game. In the greedy coloring game, the coloring must be greedy. They must use the minimum possible integer of C. So the game Grundy number gamma G of G is the minimum number of colors such that Alice has a winning strategy in the greedy coloring game. Now the variants of these coloring games. The graph YZ coloring game where Y is A or B, A for Alice, B for Bob, and Z, A, B, or no one. Y starts the game and Z may pass turns. So Alice, Bob, or no one may pass turns. Then the YZ game chromatic number, key G YZ of G is the minimum number of colors such that Alice has a winning strategy in the YZ coloring game. We omit Z when it says no one, so this notation gamma G A of G, A means that Alice starts the game and no one may pass turns is the original game chromatic number. The greedy YZ coloring game is the same idea, but the coloring must be greedy. So the YZ game Grundy number gamma G YZ of G is the minimum number of colors such that Alice has a winning strategy in the greedy YZ coloring game. So gamma G A of G, Alice starts the game and no one may pass turns is the original game Grundy number. An example for both coloring games, we have here a complete bipartite graph without a matching. If Alice starts the game, is the first to play, Bob can force n colors. For example, if Alice plays 1 here, Bob plays 1 here, and then color 1 cannot be used anymore. If Alice plays 2 here, Bob can play 2 here, and then the color 2 cannot be used anymore, and so on. So Bob can force n colors, okay? So, but if Bob is the first to play, Alice wins with only 2 colors in the set C of possible colors. In the normal game, if Bob colors 1 here, Alice colors 2 here. Then color 2 cannot be used here, color 1 cannot be used here, and then all these values will receive color 1, all these values will receive color 2. In the greedy game, if Bob colors 1 here, Alice cannot color 2 here since it's a greedy coloring, but Alice can color 1 here. So, no color 1 cannot be used here. So, since this is a greedy coloring, all these vertices will receive 1, and all these vertices will receive 2. The graph coloring game was first mentioned by Brahms and described by Gardner in 81. It was reinvented by Bodlander in 91 as the color construction game. Since then, many results appeared the game chromatic number was proved at most 4 in forest, at most 7 in outer planar graphs, a relation with the acyclic chromatic number, an upper bound in partial K trees, at most 5 in cacti, the asymptotic behavior in the random graph GNP was investigated, and the upper bound 17 in general planar graphs. So Bodlander left this question: the complexity of the color construction game is an interesting open problem. In 2015, Dunerov said that more than 2 decades later, this question remains open. Andres and Locke in 2019 introduced the variants YZ for the graph coloring game and said that the question of p-space hardness remains open for all the game variants mentioned above, including the original one. Nevertheless, in 2019, it was proved that this problem is p-space hard, solving this Bodlander 30-year question. The greedy coloring game was introduced by Raven Zhu in 2013. It was proved that the game grand number is the chromatic number in cographs, at most 3 in forest, at most 7 in partial 2 trees. They posed 2 questions. The first one was proven the negative in 2015, and the second one is still open. In the same paper of the p-space hardness of the game chromatic number, it was proved that the game grand number is p-space hard. The connected graph coloring game was introduced by Charpentier, Rocco, Herzog-Penn, and Zhu in 2019. It is similar to the original graph coloring game. Alice starts, no one may pass turns, but colored vertices must induce a connected subgraph. So the connected game chromatic number, key CG of G, is the minimum number of colors such that Alice has a winning strategy in the connected graph coloring game. They proved that Alice wins with 2 colors in bipartite graphs, with 5 colors in outer planar graphs, and in this year it was proved that there are outer planar 2 trees with key CG of G equal to 5, answering a question of this paper, the first paper. So our results. We proved that the game chromatic numbers are p-space hard for all variants YZ. The game grand numbers are p-space hard for all variants YZ. The connected game chromatic number, the original one, Alice starts and no one may pass turns, is p-space hard. Moreover, all the related decision problems are p-space complete even if the number of colors is the chromatic number. Okay, we first prove p-space hardness to the graph coloring game variant in which Bob starts and no one may pass turns. In 1999, Zhu said that the graph coloring game exhibits some strange properties, and the following apparently naive question is still open. Does Alice have a winning strategy with k plus 1 colors if she has one with k colors? This is valid when Alice starts and also when Bob starts. So we may define 3 decision problems for the graph coloring game when Bob starts. Problem 1, given G and K, the game chromatic number when Bob starts is at most K. Problem 2, given G and K, does Alice have a winning strategy with K colors when Bob starts? Problem 3, given G and the chromatic number, the game chromatic number when Bob starts is the chromatic number. Problems 1 and 2 are generalizations of problem 3 when we know the chromatic number. And if we prove that problem 3 is p-space hard, then problems 1 and 2 are also p-space hard. So we want to prove that problem 3 is p-space hard. We do this by reduction from POS-CNF B. Given a CNF formula, conjunctive normal form, with only positive literals, Bob and Alice starting with Bob, alternate turns, setting variables true or false. Alice wins if the formula is true, and Bob wins if he selects all variables of a clause. That is, Bob wins if the formula is false. Here we have an example of a CNF formula with 4 clauses, 1, 2, 3, 4. Bob has a winning strategy set in this formula, setting x5 false first. If Alice sets x1 true, she saves clauses 1 and 2. but then Bob plays false in x4, and then Alice cannot save these two clauses, just one of them. Okay? Good point of this problem, POS-CNF is P space complete. This can be proved from POS-DNF, which is P space complete. And we prove this lemma: if a player has a winning strategy in POS-CNF, then the player also has a winning strategy if the opponent may pass turns. This is an important point to the variance when some player may pass turns. One important ingredient of the reduction when Bob starts and no one may pass turns is this graph F1 here. We have a clique with k vertices, an independent set with k plus 3 vertices. So this is a clique with k plus 2 vertices, and we have this lemma. Suppose that Bob colored vertex S in his first move with color 1, for example. Alice has a winning strategy in F1 with k plus 2 colors, which is the minimum possible, if and only if she colors vertex Y first with the same color of S, that is color 1. If Alice colors Y with 1, so we can use k plus 2 colors here and Alice wins. If Alice colors vertex Y with color 2, Bob colors W with color 3, and then we have to use k plus 3 colors. Now assume, for example, that Alice played 2 in Q. Then Bob plays 1 in Q. Then in the next move, if Bob played 2 in W, he wins the game. Since color 1 and 2 cannot be used in W in Y, so Alice must color a vertex of K with color 2. Then Bob colors a vertex of Q with 3. Alice then must color 3 here. Otherwise, Bob will color W with 3. Color 1 and 3 cannot be used here. And we are done. Since Alice cannot do this forever, Bob wins the game. So this is the main idea of the reduction, the entire reduction given a CNF formula here. This is the main idea. Suppose that Bob has a winning strategy in POS-CNF B. So Bob is the first to play. He plays 1 in S. Alice must play 1 in Y. From now on, Bob will follow his strategy in POS-CNF. He wants to play in X5, so he colors X5 with color 1, which will represent false. If Alice plays here in this vertex, Bob considers that she played X1 in POS-CNF, saving these two clauses. So Bob will play in X4 in POS-CNF B. This means that he will use color 1 in X4. If Alice colored this vertex, Bob considers that she played in X3, saving this clause, but now Bob wins in this clause. This means playing X2. This means that he colored X2 with color 1. Notice that this clique, which is related to this clause, cannot use color 1 inside. So we have to use one color more. And this is the main argument, one of the main arguments of the proof. Okay? So with this, we prove that the coloring game variant, when Bob starts the game and no one may pass turns, is P space hard. Regarding the variants, when some player may pass turns, we can prove from POS-CNF when Alice starts the game, or POS-CNF B when Bob starts the game. This comes from the fact that a winning strategy in both problems implies a winning strategy if the opponent passes turns. With this, we are almost done, okay? Regarding the connected version, okay, I don't have time to show the details, but the main fact is this. We obtain P-space hardness from the variance of the graph coloring game in which Bob starts the game. Okay? This is important. G is the graph in the graph coloring game in which Bob starts, and we do this graph G prime to the connected version. We have this universal vertex here. Okay. Regarding the greedy game, when Bob starts, we obtain a reduction from POS-CNF using similar arguments, but different but similar arguments, and we prove that this variant is p-space hard, and also the variance when some player may pass turns. Okay, finally, our results. Again, we prove that game chromatic numbers are p-space hard for all variants yz. Game grand numbers are p-space hard for all variants yz. Y starts the game, z may pass turns. The connected game chromatic number is p-space hard. Alice starts the game, no one may pass turns. Moreover, all the related decision problems are p-space complete, even if the number of colors is the chromatic number. That is, thank you very much.